one dose may affect Melanie different than how it would affect Emily, right?
Mm-hmm.
And that's why it was not accurate, because it would vary from patient to patient. Alrighty. You don't need to know all of this, by the way, this is just FYI. So by the time that it was 1928, people were already using the term Rankin to sort of define a unit, but it wasn't really scientifically defined, like what exactly does a Rankin mean? So it was in use, but it was not properly defined yet. So in 1930, they came up with the concept of tolerance dose, which is basically the highest level of radiation that someone can tolerate until you start to see harm. Okay? And they measured that in Rankin. So the skin erythema dose that they previously had is replaced by the tolerance dose. Okay? And then by 1937, Rankin was internationally adopted as a measurement of exposure, and it was properly defined in scientific terms. In 1948, that's when they adopted the SI system of units. And in 1950, they had the concept of maximum permissible dose. So that is the highest dose a person can receive without the expectation of adverse biological effects. So then the idea of tolerance dose is replaced with MPD, maximal permissible dose. Okay. And then in 62, they redefined Rankin in more scientific terms. In 77, they came up with effective dose equivalent, which replaced the MPD. Okay. The ICRU, which is the International Commission on Radiological Protection, they officially adopted SI units, but the United States wanted to do their own thing, and they were still using imperial units. And then we go all the way to 91, and then the effective dose equivalent becomes the official unit that we use to describe effective dose. Yes?
So we have to know all those years?
No. I was just telling you like how it led to today.
Okay, cool. And is there an important year that we have to know?
1895.
Okay.
So all of that fun stuff led to the units and terms that we have today. So exposure, air karma, absorbed dose, equivalent dose, effective dose. Everybody's familiar with this? Yes? Hopefully. So exposure, we know that it refers to ionization that's produced in air. As X-rays pass through air, we know that it interacts with the atoms in the air. And when atoms lose electrons, they're ionized, right? And we also know that as the X-ray intensity increases, the chance of ionization also increases, right? So the amount of radiation that passes through a set volume of air can be determined by measuring the number of electron-ion pairs that it forms through ionization. So when we talk about exposure, how they actually measure that is they have a known quantity of air in per mass unit, and the total electric charge that is created is measured. That is how they come up with exposure. So what happens is they have a known quantity of air the air has a standard temperature and pressure, which is 760 millimeter Hg. You don't need to know that. And they measure the amount of electrical charges that are created in this known amount of air to come up with exposure. And this is done in a lab, so you need highly sophisticated equipment. So it's normally done in an accredited dosimetry calibration lab. Okay? You don't need to know that. So exposure, what is the SI unit for exposure? Coulombs per kilogram. And the reason why they use Coulomb is because Coulomb is the basic unit of electrical charge. And with exposure, we're measuring the amount of charges that are created in a known amount of air, which is why they use coulombs per kilogram of air. Okay? Air karma. So that is how energy is transferred from a beam of radiation to a material. So it's another SI unit. And then karma can be used to talk about any of these. Kinetic energy released in air, kinetic energy released in mass, material, or matter. And it uses gray. Joules per kilogram or gray.
So when you term your kinetic energy release, it's related to air current.
Air current.
So, in essence, air current just measures the amount of energy in air, whereas kinetic energy or.
Yeah, the amount of kinetic energy or the energy in motion that is in a mass of air. Dose area product, that is measuring the amount of energy applied to the surface of the patient's body. So dose area product, meaning dose delivered to the area, right? So sum total of air karma over the exposed area of the patient's body. The units are milligray times centimeter squared. It can be different units of grays, either milli or centi. So for example, if a patient received an air karma dose of 20 milligray and the irradiated surface is 100 centimeters squared, what would be your DAP?
Bus and it's 0.20
What would you do? Would you add the
You
numbers?
divide
Times
times
100? Wow.
because also.
So you would take your 20 milligrays times your area, that would give you your DAP. Simple as that. Absorbed dose. Do I need to repeat myself?
No.
We know that the units are gray, correct? Alright, so this is something new, quality factor. So we know that different types of radiation produces different amounts of biologic damage to the tissue, correct? So 1 gray of neutrons is more dangerous than 1 gray of X-rays. Why do you think that is?
I'm sorry, what was the question?
Higher frequency?
So 1 gray, same dose, 1 gray of neutrons is more dangerous than 1 gray of X-rays. Has a lot more energy, right? Yeah, so what they did was test the same dose on lab rats, and the 1 gray of neutrons killed the lab rats, but the 1 gray of X-rays did not. Because different amounts or different kinds of radiation energy delivers different amounts of energy. So the energy that's transferred by the radiation over a given distance, that's called linear energy transfer. That is what affects how damaging it can be. Okay? Which is why we have different weighing factors for different types of radiation, right? So it can be called quality factor or radiation weighting factor. So takeaway from this is higher LET radiation has a higher quality factor, meaning it transfers more energy, causes more harm. Equivalent dose, we know what that is. That is going to be your absorbed dose times your radiation weighting factor. The units that we use for equivalent dose is sieverts. And then radiation weighting factor, that's just another name for quality factor. So the higher the weighting factor, the more dangerous the radiation is. What's the weighting factor for X-ray? 1. This is just an example to show you what I mean. So an individual received the following absorbed dose: 0.1 gray of X radiation. Where's X-ray at? Right there. And 0.2 gray of alpha particles. 20. What is the total equivalent dose? How would we calculate this? So we have 0.1 of X-ray and we have 0.2 of alpha.
So you would do them each separately and then add them together?
So basically you would take your dose times the weighting factor, same thing. 0.1 times 1 for X-ray, 0.2 times 20 for alpha, and then you just add it together.
Are we gonna have some practice problems?
Yeah, I can give y'all some. Maybe.
So when you have two,
Yeah.
when you have, when you have,
Anyone confused?
when you have two different, types of radiation, you
Mhm.
just get the equivalent dose for each and then add together and get the total.
That is correct. That's simple. Okay, and that's just some more examples. We have 5 milligray of alpha particle. What is the equivalent dose? So we would take the 5, times it by 20, that's your equivalent dose. We have 0.2 gray of X radiation. We know that the weighting factor is 1. So we would take the 0.2 times 1, that would be your equivalent dose. But because it's asking you for milli, move the decimal 3 times to the right, that's your answer. Effective dose, we know what that is. Overall risk of exposure to humans from radiation exposure. And how do we calculate that? So it's basically your equivalent dose times the weighting factor of the tissue. And the units are sieverts. And I'll show you a math problem as an example.
The R and the W stands for what again?
Radiation weighting
Which is 1.
for X-ray, yeah. So we have 4 milligray of proton radiation exposing the gonads. Gonads are 0.08. What is the effective dose? So first, what do we have to do? The formula is absorbed dose times radiation weighting factor times the tissue weighting factor. So we have 4 times radiation weighting factor for proton is 2, and then for the gonads it is 0.08. So 4 times 2 times 0.08 is gonna give you 1.6.
Where do you
And
get the 2 from?
the 2 right here,
Yeah.
that is the radiation, or the weighting factor for proton. Cause the problem's
Oh,
saying,
okay. Protons.
Sometimes we all have slow moments, okay? And this problem, it already gives you the equivalent dose. So all you have to do is take that 8, multiply it with the tissue weighting factor for red bone marrow, which is 0.12, which would give you that.
Wait, so do we have to, are we gonna have to eventually revise those?
No, I'll give you a chart.
Okay.
Is she gonna send this part?
The registry? I doubt it.
I don't think they're gonna expect us to remember them all, so.
Yeah, I don't think they'll ask you questions like this, hopefully. All right, second last slide, collective effective dose. What do you think that means? It's in the name, collective
Collective.
effective
Collective.
dose.
Average or something.
So effective dose of a bunch of people,
Mhm.
right? And the units are man-sievert. So it's the sum of effective dose among all individuals in a group. So if 200 people receive an effective dose of 0.25 sieverts, what would be your collective effective dose?
50 million. The name is funny.
Last one, total effective dose equivalent. So this TEDE takes into account all possible sources of radiation. So it's a sum of effective dose equivalent for both external and internal source of radiation. And we know that it's 0.05 for occupational and then 0.001 for general public. And it's typically used for nuclear medicine technologists and interventional radiologists because they're exposed to a lot of radiation. Interventional radiologists, not the techs.
What was the one before this?
Collective effective dose.
So this is for more than one person.
It's for a group.
Okay.
And TEDE is for one person, but it takes into account all of the sources of radiation that one person received.
Including background?
Yes, both external and internal. And that's a wrap, folks.
When should we see that PowerPoint?